Now, in this video, we will going to discuss about the simple stress and strain. So, what is stress? The force of resistance per unit area offered by a body against deformation is known as stress. It means when the load is applied on a unit cross-sectional area which is offered by a body and which is against deformation is known as stress. Load is the external force acting on the body and it is applied on the body while the stress is induced in the material of the body. If the resistance offered by the member against deformation and the applied force or load are equal, then the load member is in equilibrium. If the resistance offered by the member against deformation, so that means when the load is applied, there will be a deformation of the member. To this deformation, the member will going to offer or the member will going to resist the deformation and the applied force. When the applied force and also the deformation becomes equal, the resistance offered by the body is equal, then the load is in or the member is it or the loaded member is in equilibrium. So what does it mean? When the column is applied with a load, but this column will going to still remains straight. That is basically because the resistance offered by the column against the external load applied. So when the external load applied and also the resistance offered by the column both are equal, then the member or the column will be in equilibrium. So that means in equilibrium, when you want to equate, the resisting force is equal to the applied force or load. So mathematically, if you write, stress will be equal to applied force by the cross-sectional area. So that is sigma is equal to P is the applied force and where A is the area of cross-section or cross-sectional area. Sigma is stress, capital A is the cross-sectional area and capital P is the applied load or the external force. So what is the unit of stress? So which is defined as the ratio of the applied load over the cross-sectional area or the applied force, which is P, divided by the area of cross-section. So since it is the area, we call it as mm square. Or it can be Newton per meter square. So what is then the conversion factors? 1 kilonewton will be equal to 1 kilo means 10 to the power of 3 Newton. 1 meganewton will be equal to 1 mega is 1 into that is 10 to the power of 6 Newton. 1 giganewton will be equal to 10 to the power of 9 Newton. So 1 Newton per mm square is equal to 1 Pascal. So 10 to the power of 6 Newton per meter square is 1 meganewton because 10 to the power of 6 is nothing but 10 to the power of 6 is nothing but mega. So 10 to the power of 6 Newton per mm square. So that means 1 meganewton per meter square. 1 meganewton per meter square, 1 Newton per meter square is equal to Pascal, therefore 1 MPa. So in other words, 10 to the power of 6 Newton per meter square can be written as 1 MPa. Similarly, 10 to the power of 9 Newton per meter square will be equal to 10 to the power of 9 is nothing but 1 giganewton per meter square, which is equal to 1 GPa. Stress in SI unit, which is measured in Newton per meter square or Newton per mm square. 1 Newton per mm square will be equal to 10 to the power of 6 Newton per meter square. How? 1 mm square, 1 mm. So it will be in terms of meter square if you want to give 1 mm will be equal to 10 to the power of minus 3 meters. So mm square will be equal to 10 to the power of minus 6 meter square. When it is taken into the numerator, 10 to the power of 6 Newton per meter square. So that will be equal to 1 meganewton per mm square. In other words, 1 Newton per mm square can be written as directly as 1 MPa. Therefore, 1 Newton per mm square will be equal to 1 meganewton per meter square, which is also equal to 1 MPa. Now comes with the next one is strain. The ratio of change in dimension of a body or deformation to the original dimension of the body is known as strain. The ratio of change in dimension of a body or deformation to the original dimension. So change in dimension of the body means it is the change in length to the original dimension of the body, which is the original length, L, which is the strain. Strain is a dimensionless and it is denoted by epsilon. So mathematically, we can write strain equals change in dimension of body or deformation divided by the original dimension of the body. So what are all the different types of stresses and strain which we are going to get it on the member? The types of stresses are the normal stress. When you talk about the normal stress, we always talk about tensile or compressive. When shear stress or tangential stress, bearing stress, bending stress, and twisting or torsional stress. Similarly, types of strain: tensile strain, compressive strain, shear strain, volumetric strain, and superficial strain. Now we will going to take up the first one, the normal stress. If the internal forces and the corresponding stresses act in a direction perpendicular to the surface, it is known as normal stress or direct stress. If the internal forces and the corresponding stresses, internal forces, that is this, corresponding stresses act in a direction perpendicular to the surface. So you can see here the force is acting in this direction, which is perpendicular to the surface. So this is the surface what we are talking about. This surface is perpendicular to the vertical plane. Perpendicular to the surface, it is known as normal stress or direct stress. Normal stress are of two types. One is the tensile stress and the other one is compressive stress. So first we are going to consider the tensile stress and tensile strain. What is tensile stress? When a body or a section is subjected to two equal and opposite pulls, so that means when a body or a section, so we consider this as a body which is subjected to two equal and opposite pulls. We can see one force is acting in this direction, so other force is acting in this direction. Both are acting opposite to each other, where the magnitudes are equal. That means here is capital P and here is also capital P. And if it tends to pull apart the particles of the material, so and if it tends to pull apart the particles of the material, causing extension in the direction of application of load. That means when the two forces which is acting opposite to each other, there will be a tends to pull apart the particles and causes the extension. That means the length of the member will going to be increased, and this increase in length will going to be in the direction of the applied load or the application of load. Then the load is tensile load and the corresponding stress is called the tensile stress. So when a body or a section is subjected to two equal and opposite pulls, that is one is this side and also other on this side, and it tends to pull apart the particles of the material, causing extension, that means increase in length in the direction of application of load. So that is in the along in the direction of the application of load. Then the load is said to be is tensile and the corresponding stress will going to be the tensile stress. Suppose now here considering a section XX as shown in the figure A. So when it comes to this, we can see here we are considering a section at XS as shown in figure A. Then the portion left of the section is in equilibrium. The portion left of the section. So now we are considering this section in equilibrium, is in equilibrium when if resisting force P dash is equal to applied force P in figure B. So that means here this member is in equilibrium only when the resisting force P dash is equal to the applied load P. How? Suppose if I consider a section here and if the load is applied in this direction, so what happens? The member will try to pull in the left direction only because there is no resisting force acting on this member. But since we say that the member is in equilibrium, when the member will be in equilibrium, when you are going to have the equal and opposite force acting in this direction. So that means we have the left direction, the body will tend to move in the left direction. I want to prevent the body to move in the left direction, and due to the application of load, the member should remain in the same position. So then when it will going to remain in the same position, you will going to have the same equal magnitude forces acting opposite to this. So that is that force is called as the resisting force, which is P dash. That means the resisting force P dash will be equal to capital P, which is the load applied. So P applied tensile force P. The portion to the right of the section, similarly, when you are considering the right of the section member, if the load is acting in this direction, then this member will try to move in the right direction. So in order to keep the body in equilibrium, then we should have the resisting force P dash, which will be having the same magnitude as that of P, will going to act in the direction opposite to the direction of the applied load, which is P, and then the body will be in equilibrium. So that means here in the figure C also, the resisting force P dash will be equal to the applied load capital P. Then let P is the applied tensile load, therefore P dash is the resisting force, capital A is the cross-sectional area of the member. So what is the tensile stress we say? It is resisting force by the cross-sectional area. So what is the resisting force? Resisting force is nothing but applied tensile load divided by the cross-sectional area. Why it is applied tensile load? Because P dash is the resisting force, applied tensile load is P, because P dash is equal to P. Therefore, we substitute the resisting force by P. Therefore, sigma will be equal to capital P by A, where sigma is the tensile stress and capital P is the applied tensile load and capital A is the cross-sectional area. Now, the next comes the tensile strain. So now we are going to discuss how the tensile strain will going to happen on the member. When a body is subjected to two equal and opposite pulls, so which is as shown, this is a body when they subjected to two equal and opposite pulls. So we have one pull in this direction and we have the other pull in this direction. That is the tensile load or the force. It causes extension. That means whatever it is shown in the red is causes the extension or increase in length of the bar. So it is naturally it will going to be the increase in length of the bar in the direction of applied load. The direction what we are applying from left to right, the extension will also take from left to right. The ratio of increase in length to the original length is known as the tensile strain. So which is that increase in length, that is the delta L to the original length. The original length is small l. So which is the tensile strain, delta L by L. That is tensile strain is defined as extension per unit length. Consider a bar which is subjected to tensile load or the force P, which is as shown in the figure. Let capital AB is the original length, which is going to small l, L, and AC is the final length, which will be final length of the bar after the application of the tensile load P. So what is the extension of the bar? which is BC, which is equal to AC minus AB. So AC minus AB is equal to BC, which is equal to delta L. Therefore, tensile strain will be equal to extension or increase in length of bar by original length of bar. Therefore, tensile strain epsilon will be equal to delta L by L. So this is about the tensile strain. In our next video, we will going to discuss about the compressive stress and compressive strain. Thank you.